Hey, welcome to TXAPA Live. My name is Jim Warren with TXAPA. Today we've got Travis Patton, who's the Flexible Pavement Section Director. Did I get that right?
That's right.
With TxDOT and MTD. Welcome, Travis.
Thank you for having me.
Well, welcome. We're glad to have you here. We're in TXAPA's original studio here. We've got two now on our campus. And we're here today to talk about the overlay test and some evolutions that's been going on there. So what's the overlay test?
So the overlay test is the cracking test that TxDOT developed, and it's probably been close to 40 years ago.
Really? Wow.
And it was originally invented to model reflective cracking. So when we place hot mix on top of jointed concrete pavement and that concrete continually moves back and forth,
right?
Can we get rid of that constant the whole way by putting a nice hot mix overlay on it?
That makes sense. That makes sense. And that is emulated actually in the test.
That's right.
Because that's how that test is actually oriented.
That's right.
Okay, so it's been around a long time. It's working.
It's working.
And at least from some national research that's been going around, because there's a lot of work nationally being done on the holy grail on asphalt performance is kind of like the cracking test. And there's lots of different cracking tests depending what state you're in. Texas has been a long time, obviously, with the overlay test. And a lot of the work that's being done recently, there was a really big research project at NCAT. And you're familiar with the National Center for Asphalt Technology. And they've kind of come down with the top couple tests that they think really are promising, and guess overlay test is on there.
Yeah.
So that's awesome. That's awesome. So there's been some changes in the overlay test process or the data. So right now, or up to this point, we're using cycles to failure.
Correct.
Right, and it was 300?
So the way the test used to run is it would look for a 93% reduction in initial load.
Okay.
Or it would go to 1,000 cycles.
Or to 1,000 cycles.
And that was how the test would end. So if you had something very, very flexible, like a rubber band, it would go 1,000 cycles and it would take all day to run.
Okay.
If it was something very stiff, like maybe say concrete, and the machine could physically test it, it would have an extremely high load because it is strain displacement, meaning it's going to open up a 0.025 gap, 0.025 inches
each time it cycles.
Every single time.
Okay.
So if you're very, very stiff, same displacement every time. So the very first one would go extremely high load, it would break that concrete, and then that second one, it would be failed.
It would be done.
And if you look at it from just a logical perspective, if you have a rubber band that only had 5 pounds on it ever, to open and close that 0.025 inches. That concrete may have had 10,000 pounds.
Right.
Even when it failed, it may have had 5 pounds, and it was still superior than that rubber band. So it was somewhat flawed from the beginning.
Okay.
And the fact that you were penalized based on that initial load.
Okay. So that kind of begat the idea of maybe we need to look at this a little bit differently.
That's right.
So how did when did that process start? Who did the work? And where are we at with it?
Yeah, so originally the overlay, like I said, maybe 40 years ago was invented at TTI at A&M. More recently, we had a project with UTEP, UT El Paso. That was probably around 2014, 2015 that we started looking at it.
6, 7, 8 years
and so
ago.
what we did to start this project is we got every known overlay producer and had a machine shipped to UTEP.
Okay.
And we took all of our existing data at MTD. Well, we run a lot of informational stuff, and everybody wonders, what are we ever going to use it? Well, we did use it. We sent 10,000 or so data points over to UTEP, and they were able to go through there and look at existing, because we still have the raw data file. They're able to crunch it under a new method that they later developed.
So we're not talking about a new method, we're just reprocessing
the data.
Okay, so you're able to use all that data.
We capture all of the data. So the way it's
awesome.
actually being run is no different than the way it was being run from day one.
Okay.
The only difference is how we analyze it.
Wow, well that's awesome, because a lot of times you end up with a whole new method, and then you got to go collect all new data, and that could take years to validate it. And if you're able to go back and use all the existing data and just reprocess, that's an awesome way of doing it. Yeah. So what did we come up with? What's the new ideas?
So as I mentioned, the original one was number of cycles. And with number of cycles, inherently flawed based on that first, right? Because it's 93% reduction in initial load.
Okay.
So initial load, if it fails, it's done.
Okay.
The new method actually breaks it into two parameters. We've got critical fracture energy, which is the amount of energy it takes to actually start that crack.
Okay, so we got, and it's CFE, right?
Correct.
Critical fracture energy. So remember that, not remember that. There'll be a quiz later, okay?
And then the other one is crack progression rate, CPR.
That's not this kind of, no.
Not that kind.
Okay. So when we've got our sample, right, and the way they do that is they glue it down to a platen, right, and they glue the other side down to the platen, and then there's a notch. That's not the scale, but this one becomes fixed, right?
Correct.
And then this one is actually moving 0.025 inches each cycle.
Correct.
And so you're trying to induce a crack at that point. So the critical fracture energy is the amount of energy or work that it takes to actually initiate that crack right at that surface.
That's right.
Right? And then the crack progression rate is how much energy it takes for that to go through. So we're not looking at a percent reduction, it just goes through then.
That's right. So whereas we were treating it with the one variable, now we've broken it into two different phenomena, right? So you are going to get a benefit of having something a little bit stiffer from the perspective of it took more to break it.
Right.
However, if it's too brittle, it is just going to, the rate will be extremely high.
So there's a balance
There's
here.
a balance between the two.
Okay.
So can we prevent the crack? And then when it does form, can we prevent the rate of growth?
Okay. So the energy then would be, I guess, related to the mix stiffness and the binder stiffness initially, right? Is that what I'm thinking?
So there's a study through UTEP, and they broke it down by coarse aggregate, fine aggregate, binder types, binder grades, binder contents.
Okay.
One of the largest, which I think we all care about, right, is the amount of binder.
Okay.
So it's very sensitive now to the amount of binder. So
this is sensitive to.
So these are both going to be. This is really going to come down to overall structure. Okay. This one right here is going to come down to the binder itself. Okay.
So we're talking about the binder content, and I think you mentioned earlier actually almost the film thickness concept.
The film thickness concept.
Well, that goes way back.
It does.
But I get, sometimes I guess we keep recycling stuff. We bring stuff back around in the process. So it's always made sense because, we're in our studio and we teach in some of these classes about, if your film thickness is really thin, and that's why our dense graded mixes, we want to make sure we compact them because the film thickness is generally pretty thin. And we don't want air and water going through the pavement because that oxidizes the layer and then causes it to fail.
That's right.
Okay, and that's different than like an SMA, which has got a thicker film. But, that does kind of make sense of having, again, understanding that whole film thickness concept. So, well, that's cool. So what kind of numbers these are numbers or percentages or are they, or is it just an index or is it actually a value?
There are numbers. We are still playing with where they need to be for each type of mix. Okay. Historically, we did run informational on our dense graded and our super pave. Mm-hmm. We found a cracking test and we said, let's apply it to everything.
Sure. Yeah.
And so we've kind of pulled back on that, but we are reassessing values on those and to see in the future if we have limits, what would they look like?
Okay. Okay.
Mixtures like Tom have always had an overlay requirement. Okay. So we've essentially taken the equivalent of that in the critical fracture energy and the crack progression rate and applied that to the current special specification. Okay.
So we got a Tom mix, obviously thin, inch thick. It's got what, 7622 in it, PG 7622 binder. It's designed to be placed. It's designed to have some flexibility, shall we say. As maybe in lieu of a seal coat or or more of a preventive maintenance type system. I'm making that material. What do I need to be careful about when I'm making it so I don't impact these numbers.
And I'll tell you, Tom is unique as well in the fact that it does not allow recycle. So in some of our mixtures, the balance is you can use recycle, but you need to do it wisely. So you're balancing it with the amount of virgin binder. The rest of the nation, for the most part, uses the effective binder content. TxDOT doesn't do that. So you could design mixtures with 30-40% wrap, which we're seeing in the balanced mix design, as long as they still have enough effective binder. Meaning it has enough virgin binder to allow that flexibility,
to give that
glue to hold
the whole thing together.
So it can be done. We are seeing that in the balanced mix design, and I think that's what we'll see moving forward is, you know, where we foresee this going is utilizing this test along with the Hamburg, and as long as you're balancing performance.
Balancing the rutting and the cracking criteria.
Then we open up the specification at some point to allow different amounts of recycle. And
now that once you develop comfort in, hey, I'm comfortable with the results that I'm looking for, now I can start changing some of the inputs to give me really more what I'm looking for. And I think, you know, if we can add some recycle, you know, get our recycle values up a little bit, I think it helps sustainability, recyclability, all that sort of stuff. And, you know, we're talking lately about just supply chain, about just aggregate quantities and getting material. Everybody's so busy. You know, and if we've got mountains of wrap just sitting around, at some point we need to figure out a way of using that material. So that's a good thing. That's a good thing. So I think that, and we haven't talked about balanced mix design yet. That'll maybe another program we can do. Maybe get John Epps in here and maybe some other folks to kind of talk about that. But that's an effort to kind of, as Travis mentioned, to find this balance during mix design and during production of the rutting resistance of the mix and also the crack resistance of the mix. And I think what we're finding is we've actually got a meeting coming up on that, and I think they're finding some interesting ideas out of that. So we're excited about that. So, so we've got the overlay test. We've got two new terms. We're measuring something different. What's another advantage of the overlay test by using this versus the old way?
I'm actually really glad you asked that because I actually wanted to show this. So if you look at the loading curve of a traditional overlay, it's going to look like this. And so the problem was we run sample 1, and let's say it goes 1,000 cycles. The next one is going to look like this. And it went 500 cycles. And then the next one was maybe right here. And let's say that was 300 cycles. So the way our old method would work is we would say, you average those three and do you meet the minimum cycle requirement? And we see much more severe than this, where you have maybe 10 cycles and 1,000.
So the repeatability is all over the place.
The repeatability was all over the place. The coefficient of variation on some was upwards of 80%.
That's not good.
That's not good. So very high. Another issue under the old method, like I said, it would go 93% load reduction based on that initial load, or 1,000 cycles. So 1,000 cycles, it'll take you 3 or 4 hours to run one sample. Right, because you also have to condition these. So it'll take one machine. It will take you all day to run.
You're tied up one machine.
A good mixture.
One machine all day.
All day.
How many do you have at MTD?
We have 4.
So that's potentially 4 samples a day.
That's correct. So and then back to the variability, you notice, right? So under the new method, really what we're doing with these two parameters.
You want to erase or are you good?
No, we're fine. So with this new method, essentially what we're doing with these two parameters is defining the shape of this curve. So you'll notice within, say, this region right here, they're the same. Right, and maybe my thing is perfectly to scale. Until they start to divert, there's a point where they all act identical.
So we're measuring in that area. We're looking at the performance.
These two right here
are measuring the performance in that
within
area.
Within the first 30 to 50 cycles, will establish the shape of that curve.
So that's going to speed up significantly.
That's right. So the next step in this process, as we get out of our old specifications, we do have some ongoing projects that still call out cycles. So we're still running them for the sake of that.
But you still have the data that you can measure this though, right? Just by reprocessing,
the machines now all have the software where it'll give you the cycles and it will give you both of these. So we actually, that was one of the benefits of the UTEP study, is they were working with the manufacturer, and the manufacturer actually built in their
software?
all of their stuff into their software. So,
But there's no, is there a relationship between number of cycles to these numbers, or maybe?
loosely.
But because you're looking at this area versus this area.
That's right.
So you're
That's
not really
right.
looking at the same thing.
That's right. There is a loose correlation.
So for our guys who are used to saying, hey, our numbers are out here, that doesn't necessarily mean the same thing. But if you're getting numbers out here, are you going to get decent numbers here?
So part of the study and what they were looking at was if you run it the new method versus the old method, keeping in mind we just used the same data set and analyzed it two different ways, that most of them were still meeting this.
Okay.
So they do have a loose correlation on the critical fracture energy and how many cycles that roughly equates to.
Okay.
And then the CPR, they have a relation as well, and I believe with that they're relating it more to the IDT. So you're looking at the 80 to 200.
Okay.
PSI on the IDT.
Okay.
So
Okay.
they do have a correlation, and they're trying to relate it back to tests we already run. But back to this, one of the big benefits will be we can actually set the machines to cut off at, say, 200 cycles.
Because you've already collected this data.
We've already collected what we need.
And you don't need to go any further.
That's right.
So
So
now
the
you're
beauty will
picking
be
up-
we can do 5 times as many samples per machine.
And you don't have to sit there and wait for the thing, and you can go off and do it, and it shuts down when it's done, and then you come back and
That's right.
reload new samples, and your productivity should go up
Should
significantly.
go way up.
Awesome.
So
Awesome.
huge benefit.
Okay. So right now we've got this is not in the supplemental specifications that just came out, or the supplemental specifications for April. This is only in what mixes?
This is definitely in Tom.
And
I believe
thin
it's
bonded, or is it an SMA?
I thought it was an SMA, but
Okay.
I will say that we had them. Don't quote me.
Yeah.
We had them in a few of our specifications.
And then we removed
And
it.
then we did remove them, stating that we would gather more data before
Right.
we implemented an actual number, but I do
Right.
know it's in Tom.
Okay, perfect. So we will be you'll see that as we go forward, if you're doing Tom mixes, we'll actually be collecting this data, and obviously TxDOT is evolving with this information, and we'll be able to kind of figure out where the final number is going to be at some point. Well, that's cool. So I'm a contractor, and I've got to make a design, and I'm interested in making a mix long-term that's going to meet these criteria. I want to be proactive. I want to be forward-thinking here. Can I get this machine to do this yet?
So,
Can I do it myself yet?
Well, we are actually working on that.
Okay.
We are working on that.
Okay.
So we're working with UTEP right now. We're doing a variability study amongst different machines.
The different manufacturers?
Well, right now there's really only one manufacturer that's
Okay.
still around.
Okay.
So historically, MTD has used our machines for all of mixed design approval.
Right.
So there's at least the level of consistency.
You've been the standard up to
At
this
least
point.
some level of consistency
Okay.
because of that.
Okay.
We've been working with the manufacturer. We do have a new calibration jig to verify the equipment, which has always been an issue.
Okay.
We've got a calibration procedure that we're working on to come out. And then we've got a variability study, both internal and external, meaning across laboratories. So
The other districts that have the overlay test?
well, even contractors
And
as
even-
well.
so we have some-
So
okay,
when
okay.
I had the manufacturer fly into the States, and he visited about 8 labs.
Okay.
Most of those were contractor labs.
Okay, so we're in that process of trying to develop, whenever you develop a test procedure, you do these variability studies to figure out, if I run the test and you run the test on the same machine, we're going to get a certain amount of variability. If I run the test on my machine and you run a test on your machine, we're going to get a different level of variability. But we would need to know what those numbers are before we kind of let the dog loose, if you will.
That's right.
Ran through the same thing with the Hamburg, right?
Yeah, absolutely.
So is it long-term kind of the same ideas to maybe have these out there where folks can run them themselves and figure out what they want?
That's exactly
Okay,
right. So
okay.
our plan right now, those 8 or so contractor machines across the state, we did have the calibration jig
Okay,
put on those. The
Okay.
manufacturer put them all within the same tolerance of each other.
so they've set them.
They've already set them internally.
Okay.
And then our next
Okay.
step, we're hoping within the month, we've got 3 different mixes coming from UTEP.
So you're going to do a round robin?
And we're going to do a round robin, and
Okay.
we're actually going to do Hamburg, overlay, ideal CT, and ideal RT.
Okay.
And so we're going to try to capture all of them within the balanced mix design project.
Perfect.
So we will be sending out some material to.
Good.
We're hoping 10 machines per Hamburg, 10 machines
Okay.
per overlay.
And the round robin is just a matter of we're gonna take the same material, mix it up, and send that out to run on multiple machines. And then to do that, you'll be able to, you're trying to eliminate the material variability out of the equation. So we're really just testing the machine variability so we can figure out how close they are and what, because you don't, like you said, you don't want to have something that's got this amount of range. Right. It's like, well, I got 100, you got 1,000. Okay, we're close enough, and it doesn't really mean anything.
That's right.
So as we can refine that in that process, that makes sense where we can really kind of tie that thing together. So, cool. So what do I need to do today? You say I don't have the machine. I don't have the machine yet. Okay, because not all the contractors have it. But if I'm thinking about my mixes and thinking about, we're going to go balance mix design at some point. We got these pilot projects out there that we're working on. What can I do today to my mixes to help improve these numbers, maybe potentially? Right now, I've got mix designs. I got this season's coming. It's May. We're ready to start paving. I got to do mix designs. Got to send them to you, send them to the district. What do I need to do? What things have you seen based on what you've seen so far? How can I make these numbers better?
Use more binder.
Use more binder. Okay. So I got to make space in the mix.
That's right.
So is my VMA going to go up then?
Probably.
Probably. Okay.
Probably.
So I've got to, but if I use more binder, binder's expensive.
It is expensive. So I will say part of the balanced mix design is how do we balance this economic portion with the performance. So I do think that's the key. Obviously, the easy button would be put as much virgin binder in there as possible. You could probably pass this very easily, but maybe not economically.
Does using like a 76 versus a 64 give me the ability to use less binder, or is it really truly how much binder is in there?
I would have to go back and look at the data to know exactly.
Okay.
It's been a few years since I looked at the polymer data.
Okay.
I want to say that there was a benefit utilizing
some
higher grade binders, but I couldn't give you a number.
But it doesn't replace the amount of binder.
It's really driven by the amount of
binder. So that's, again, that's one thing that we got to watch is not, in a competitive environment, it's going to be a challenge, but I think long term, once we establish these numbers and we can actually measure that, then you'll have to end up doing that. But that's something we need to think about as we move forward with this process, is figuring out a way to get more binder in the mix and in the process, virgin binder. So again, we want that film, we want that film thickness, if you will, around the aggregate. So if we can do that, I think we'll be in a better place. But again, it's a balancing act, as you said.
It will be balancing, and I think the other one that people don't talk about is economics. I know in industry we do talk about it, but I think when we're thinking performance, we balance Hamburg and overlay, but the real other variable there is economics as well.
Yeah, I mean, you could do the best of the best of the best, and all of a sudden it costs X amount of dollars a ton. And it's like, well, we can't afford to make that.
That's right.
So we got to find that balance, and if we can find a way to get our wrap content to a reasonable level. Again, I call it responsible use. I think you used the same word a little bit earlier. Responsible use of recycle. Get enough virgin binder and to get everything stuck together properly, and get those benefits of reducing that initiation point where we don't want. If we can get it to the point where it never does that, we don't have to worry about progression rate.
No, that's right.
Right?
That's right.
So, and that's really kind of the idea with some of the concepts of the long life pavements, of getting them thick enough and loading them properly, where we get our tensile stresses low enough at this interface where we don't end up having a problem. And so that's one of our big challenges with this process. So, cool stuff. Cool stuff. So the amount of binder, does it? And obviously, we're probably going to need to change our gradation a little bit, just to make some space.
And when we've done that a little bit on SuperPave, so as I mentioned, we do have ongoing studies looking at this.
Okay.
And so we won't know,
for a while yet.
for a little bit.
Yeah.
I will say one of our issues of getting this balance has always been the repeatability of this test.
Yeah, I mean, if you're seeing numbers like that.
80% different, how can you ever find a target to hit if you can't keep a consistent target?
Are you more comfortable with these numbers? Even though you're measuring in this range, that it's actually telling us something?
The variability on this is about 10%.
Wow.
Coefficient of variation.
Wow.
Whereas this was upwards of 80.
Oh, okay. Well, that's huge.
So we're very, yeah, we feel very good that we're consistent. Now can we specify what we think, I mean, where we've currently set we think is going to give us quality, but is that too far one way or the other? Can we push the envelope a little bit more and get higher performance? Are we specifying too much and therefore it's hitting economics?
Okay.
Do we need to go back the other direction a little bit? And that's what we're trying to fine tune right now.
And that makes sense. That absolutely makes sense. We appreciate that.
Yeah.
We appreciate that because we don't want to have to all of a sudden, blow the whole thing up. If we can make a final little adjustment, again, if we're having tests with low repeat, with small variation, small repeatability is always kind of like, that's it, brother. If we hit that, we're good to go. Having something like that makes sense. So, was it worth it to go from this to this?
I think so.
Yeah. Okay.
I think so.
Okay. And then you mentioned a couple other tests that are kind of going on behind the scenes with the balanced mix design, and one of them is called Ideal CT, and the other one is Ideal. Since we're just talking about stuff today,
yeah.
What's the difference between these two?
So the CT is a cracking test, and the RT is a rutting test.
Okay, and the cracking test is basically using kind of an indirect tensile.
It's identical.
Right?
It's identical, except it has an LVDT. The only difference.
So we're loading it this way, and we're trying to induce a crack this way, and the RT is the rutting test, and that has more of a. I'm not a good artist, but it kind of grabs it around the part of the circumference to create kind of a shear.
It has more of a shearing effect, and then like you mentioned, this one will have a vertical crack or indirect tensile as these two sides are trying to oppose each other, literally just pulling it apart.
As they're trying to go this way.
That's right.
Right? And these are actually trying to go kind of that way, and it's creating internal shear, which would be displacement, which would be rutting. Okay. Where did these come from?
So both of these tests came from TTI.
TTI again.
So we did have a research study with them, and the main point here was we wanted something that was quick,
right?
Something that was repeatable,
right? Something
that was cheap. So one of the issues with really all cracking tests on a national basis is the sample preparation.
Right. Because the overlay test there's a lot of cutting.
Cut them, check density.
Yeah.
Dry them back, epoxy.
Right.
And then if you look at some of the other ones, right, that they drill holes in them,
they slice them. They got to put a crack groove in them, all this sort of stuff.
A lot of sample prep.
You're just using you're compacting a smaller sample. Was it 65, something like that?
Yeah, it's the 63 millimeter, 62 millimeter.
62 millimeters in thickness, which is what, 2.5? 2.5 inches.
Yeah.
As opposed to 4.25. And we're using it as is. There's no cutting, there's no drilling, there's no processing, so the time lapse is tremendously better.
Really, there's not really that much conditioning either.
Okay.
So
and I think that's been kind of one of the challenges is in cracking, you're trying to look for how the mix is going to perform years down the road, right? And so there's always been this, what do we do about aging? Because you take fresh mix, it's the best of the condition.
Yeah.
But what we're saying is with some minimal conditioning, running it through this way and then looking at the data through this, and that was Fuji, wasn't it?
That was Fuji.
Fuji's Al.
Yeah.
Good job, Fuji. And then he's kind of came up with this idea to kind of give us both terms. And the rutting test, from at least I've seen, is they can take that material, compact it, and they can run it within an hour or two. So we're almost to the point of I'm not going to say real time, but it's close to real time performance testing as we possibly get. So is there a correlation between this and this?
And so right now we are still looking at that. There's not a direct correlation like we would have liked to see, meaning a value of 100 on this equates to some number on this.
Right.
And it's not like that always, but it seems to be that way for a given mix. Meaning, so if you test it up front and compare these two on a given mix, throughout the production, the relationship between the two should be very similar.
So maybe we do this at design.
And so that's what we're considering on the balanced mix design.
And then long term, maybe we run this during production.
So on the balanced mix design, what we're doing right now is we're designing based on this. We're balancing it with the Hamburg. Once we have passing, then we're running an ideal CT during that same period of time, and we're getting a correlation. And then during production, we're just running this. We say as long as it doesn't go over that,
X or Y,
limit, you're good. If it does, then you need to go back and verify with an overlay.
Well, that's really not much dissimilar than what we do with a core and we do with a gauge in the field, right? We take our nuclear gauges and we set them on the ground and we get values and then we compare that to the core values and we develop a correlation or an offset. So it's the same, to me, it's kind of the same idea.
That's right.
That, we're saying that the core is gospel or whatever, and this is, this is the best we can get, but then this is quick. It's rapid, and I'd rather have maybe a bunch of these than maybe one of these a week. I could have one of these a day.
You can run those. If you've ever run an IDT, you can run this in a minute.
Yeah, they just stick it in there as long as it's aligned properly, hit the button, it's done. Yeah.
That's it. And like I said, that's the only difference, except there's an LVDT that measures the displacement.
Okay, so we're really looking at fine gradations of displacement.
That's right.
Okay. Well, cool. Well, that's what's going on. What else do we want to talk about with overlay test?
I think we've covered it pretty good.
We beat it up, huh? All right. So, hey, that's TXAPA Live for today. Big thanks to Travis Patton for coming out and spending some time with us. A lot of really cool stuff going on. I think there's a lot of work being done with this to really help move the cheese, if you will. But move the cheese in a way where we're improving performance, and we're getting to more of the root of the issue. And we're refining. We're getting rid of something that's been around a long time, but we're not getting rid of it. We're just reinterpreting it, which was brilliant, as opposed to starting all over. And now we've got the overlay test part 2, it's got a new jig, it's got new materials, and we'd have to start all over with new data collection and everything. So that's brilliant. So thank you for coming out.
Yeah, thank you.
Appreciate you. All right, so that's it for today. We appreciate you coming out. Look forward to next time at TXAPA Live. Take care, everybody.